All right, now that's enough room. Okay, so is that mine? All right. And the sodium chloride, do we care about sodium chloride? No, because sodium chloride is not going to change the pH. All right, and so what we do here is we know this. This is equal to the sodium hydroxide concentration at equilibrium. And then we make an assumption. You know, at this high of pH, you know, the pH was, what was the pH in this particular problem? 10.80. At a pH of 10.80, is water going to be a significant contributor to this? No, not at all. Well, you think, well, shouldn't water be a significant contributor? Because if the pH is 10.80, that means the hydronium ion concentration is 10 to the minus 10.80, which is equal to what? Can somebody just punch that out? Oh, I got a calculator here. Okay. Molar.
That's 6.309 times 10 times 10 to 10.
Times 10 to the minus 10?
No, positive 10.
Oh, 10 to the positive 10 can't be right.
1.58 times 10 to the negative 11.
1.58 times 10 to the negative 11 molar hydronium. So if the hydronium is 10 to the minus 11 molar, what's the most I'm going to get from water? 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. Is that going to be significant or insignificant?
Significant.
It's going to be hugely significant, right?
Yes.
And so if hydronium from water should be hugely significant here, then I should do step 2, correct? No, why?
You have the hydroxide?
Yeah, right. I don't care what the hydronium is because this is a base solution. Base solution, I'm looking for hydroxide ion contributors. I shouldn't be considering the hydronium ion contribution from water because I got a base solution, and I should be looking at the hydroxide contribution of water.
Ah.
And so if the hydronium concentration is this, what is the hydroxide? Well, that means the POH is 3.20, which means that the hydroxide ion concentration is actually
6.309 times 10 to the negative 4.
times 10 to the negative 4 molar. Now is water going to be a significant contributor to hydroxide in this solution? No, totally insignificant. And so that's because this is a base solution. Base solutions we're looking at hydroxide, not hydronium, right? And so this is why, okay, this is why I'm going to ignore KW because it's not going to be significant here. I'm going to stop here. There's no further reaction because I'm left with a neutral salt and a strong base. And so I can ignore the neutral salt and just call this a strong base solution. Well, that's going to be this concentration here. So we know this, and so this is going to equal the sodium hydroxide concentration, which is going to be 20.00 divided by 20.00 plus Z, minus the HCl concentration, which is going to be Z over 20.00 plus Z. And so we just solve for Z, right? Solve for Z. And so this is what I mean by working backwards, because we're starting at the end here, and we just work back to the beginning. Okay, is that okay?
Why do the initial hydroxide and hydroxide concentration changes over time? Like, why is it not always?
You know, I missed something though.
I guess the molarities.
I missed the molarities here.
So you got, that was just what
0.200, right?
0.200 on the HCl and 0.175 on the
175 around NaOH, yeah.
You gotta change those top numbers.
Yeah.
No, on your formula by your hand. It can't be 20, it has to be
Times.
molarity or something.
Right, times 0.175. This one needs to be times 0.175. This one needs to be times 0.200. I forgot those.
There we go.
Then that works. What was the question again? I'm sorry.
Why can't the initial concentration of NaOH be always 0.175 molar?
We have two initials here. The original concentration of the NaOH,
That's
0.175, and then we got to add HCl to this. When we add the HCl, the volume is increasing. You know, no longer is it going to be 20 milliliters, it's going to be now much more because we added a bunch of water. And so it can't be 0.175 anymore. But the problem is I don't know how much extra water I added from the HCl because that's what we're trying to calculate.
Uh-huh.
Does that make sense?
Yes.
Okay. Okay, so yeah, because it's solution dilution. So this is what I do. You know, if we skip millimoles, if we skip directly to millimoles, we don't have to do solution dilution. And then what we do is we calculate the diluted concentration at the end, you know. But, you know, the reason I do this one is because I don't want to spend a lot of time looking at a whole bunch of different ways of solving these. I just want one way, and this way you could do, you know, going backwards or forwards. Doesn't matter.
Are we gonna have a test on Thursday?
Well, I was thinking the test will be on Tuesday. Is that, what's that? No, next week. I still, unless, is that too late or too late? After that spring break, a lot of stuff fades from memory, you know, right? Or do you want it sooner, like tomorrow, while it's still fresh in your memory? Or Thursday? All right, then the plan is that I split up the kinetics lab over 2 days, but we're just going to do it. It's only a 1-day experiment, so we'll do it on Thursday. And tomorrow I'm going to use for some catch up and some other stuff, talk about lab.
Doesn't need anything new in our.
You don't have to prep for this one.
Lecture?
Computer lab is next week. Is computer lab. We're going to, in the computer lab, we're going to work up 2 experiments. We're going to plot the data from the titration lab, and we're going to plot the data from the kinetics lab, both of those. We can do those in 1 day. All right, do you know the only difference? The only difference between B and C is this.
You're solving for pH instead of pH.
Right, well, actually, I should say there are more than one difference, but the main difference here is that the HCl is not the limiting reagent. HCl is going to be the excess, so the NaOH will be the limiting reagent, right? And so this is going to go to 0. This is going to be HCl initial minus NaOH initial.
Yes.
And then we solve for the pH, which gives us the hydronium ion concentration at equilibrium, which is equal to this, and then we solve for Z.
They said
Okay.
the reverse those numbers.
So do you need me to set it up, or are you okay?
I'm okay now.
Okay. Anybody else? You're okay? All right, this is an example of a strong acid, strong base, where we know where the equivalence point is roughly. Usually we try to figure out, when we're going backwards like this, we try to figure out where we are on the titration curve. And so when we have a polyprotic acid, let's look at polyprotic acid, so a strong base. You know, we're going to see more than one hump. So if we look at some diprotic acid, like we'll call it H2A, being titrated with sodium hydroxide, we're going to see a first equivalence point and then a second equivalence point. When we look at the volume of the sodium hydroxide, you know, this would be the equivalence point 1 here. This would be equivalence point 2 here. And so let's say if equivalence point 2 came in at 30.00 milliliters, then equivalence point 1 must come at 15. This is stoichiometry, 15.00 milliliters. Some of these points are going to be pretty quick. For example, what we call the half equivalence point 1. And so this would be 1/2 the equivalence point 1. This is going to be pKa1 of the acid. And then if we go over here to the half equivalence point 2, and so we take this and divide it in half, we'll get the half equivalence point 2. This is going to be equal to the pKa2. Usually the first one here, this is going to be HA minus at the equivalence point. HA minus, this is amphoteric salt. HA minus, the pH is going to equal to pKa1 plus pKa2 divided by 2, and this is going to be at a pH less than 7. So for diprotic acids, the first equivalent point happens in the acidic region, and over here we're going to have A2 minus. This is just a dibasic salt. And so here, if it's dibasic salt, pH is going to be greater than 7 here. And so we could do some example calculations. We could do some example calculations about how many milliliters it might take to hit a certain pH. So we should pick an acid here. And so let me grab an acid that we can. Let's try, which one do you want to do? Let's try sulfurous acid. Maybe that's not so, or,
For sulfuric acid and a strong base, they were assuming that sulfuric acid was going to be completely ionized, both ions. Is that the assumption?
no. There's a,
But they were doing that.
which problem was that?
It was in the beginning, there.
No. No, we wouldn't do it that way.
No.
Yeah. It depends on, what did they use the calculation for, pH? All right, we could do, you want to do sulfuric acid for this?
Yeah,
We can do sulfuric acid. Sulfuric acid is a little bit tricky because the amphoteric is so heavily biased towards the acid, because the Ka is much, much bigger than the Kb for that. In fact, the Kb is sulfuric acid. Yeah.
Yeah, it's 37 on the book.
37? Okay, let's take a look at that. $37. Two aqueous solutions are mixed. 50.00 milliliters of 50. What is the pH of the resulting solution? All right. I'm gonna do this a little differently than their buck. We're gonna make this into a titration problem. We'll calculate some other pHs along the way. And so here, what we'll do is we'll put the acid in the flask here. We're gonna put 50.0 milliliters of 0.0150 molar H2SO4. And then we're gonna titrate it with 0.0385 molar NaOH. Here. Which is going to change our volumes here for the chart. The tricky thing about this is, what about pKa1 and this? The problem with this is this. you know, for sulfuric acid, H2SO4, you know, Ka1 is equal to what? Very large. And then Ka2 is actually pretty big itself, 0.011 or 1.1 times 10 to the minus 2. Okay, so that's going to make this, okay, if Ka is very large, what is the pKa? You know, pKa1 for this?
Very small.
pKa1 would be the negative log of the Ka, so, you know, what is the negative log of very large? Very small? Is it?
Let's see.
And then, well, this one isn't so bad. We can figure out what pKa2 is. And so what is pKa2 of this? It'd just be the negative log of 0.011, which is going to give us, what? 1.95. And so here we should be at 1.95. And then we think about this. Well, I know if this is an amphoteric, this is going to be salt and water. And the salt here, in this case, is going to be HSO4 minus, or sodium hydrogen sulfate in water, at the first equivalent. So we've neutralized the first proton, and we're left with this. At the second equivalence point, we're just going to have sulfate because we've neutralized both protons. And so HSO4 minus, well, the pH of the amphoteric, like HSO4 minus, is going to equal the pKa of HSO4 minus plus the pKa of its conjugate acid, which is H2SO4, divided by 2, right? That's what we should get, but what is the pKa of H2SO4? You know, we have a problem there, right? So we have a problem there, and so, but this is something that's not too difficult. And so what we do is we just fall back on a way that works, for all the problems that you're going to solve. And what way is that? Well, we don't have to do these shortcuts. These are shortcuts, right? What we do is we just fall back on our standard problem-solving method. Our standard problem-solving method works. It should work for all of these. And so what is our standard problem-solving method? Well, we do step I, which is going to be solution dilution, and then etc. And so in this particular problem, the way I'd handle it is just like any other titration problem, except, you know, in this case, we're adding 50.0 milliliters of this here. And so what we're going to end up with is 100 milliliters, right? This is also very unusual. In a titration, to have 1 decimal place is pretty much a worthless titration. You know, that for precision, right? We can easily get 1 more decimal place using a burette. But anyway, this is what they have. And so the first step is to do solution dilution. So the solution dilution here is easy because it's a 50 to 100 dilution of 0.0150. This is going to be half that, so it's 0.00750 to keep the sig figs. And then the NaOH isn't going to be as easy because the number's not as clean. So what's half of 385? 192.5?
Yeah.
0.01925.
Yep.
All right, then what we do here is we just take the strongest acid, which is H2SO4, plus the strongest base, NaOH. Now, we do this differently than we would in a metathesis problem. Like in Chem 1A, what you do is you take 2 sodium hydroxides, neutralize both those acids, right? No, what we do is we do it in steps. So we'll take the strongest acid, H2SO4, and neutralize one of those. So what we're going to end up with is NaHSO4, or sodium hydrogen sulfate, the amphoteric solid in the water, H2O liquid. And so the H2SO4 is going to be 0.0750 molar, the NaOH is 0.01925 molar, and this is 0. Now, what is K for this equation here? K is not just very large, not just very, very large. Not very, 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 very large. It's very, very, very large, right? This is just to keep it in perspective, because this is a strong acid reacting with a strong base, and so it's got to be huge. What's the excess? What's the limiting? H2SO4 is the excess, 0.00750, which is 5 times 7, 8, 1.
Wait, how come? I thought the NaOH was limiting.
Yeah, we have excess NaOH here.
Okay.
All right, this is what we call step 1. In step 2, we look at what we have left over. What kind of mixture do we have left over? Well, when we look at the mixture that's left over, it's a strong base with an amphoteric. An amphoteric can either be an acid or base. In this case, if we have a strong base, the strongest acid that's going to be present will be the amphoteric species. So we take the strongest acid present, which is going to be the sodium hydrogen sulfate, which is a decent strength acid with sodium hydroxide. So this would be step 2. In other words, for each step, we just always do the same thing. It's the strongest acid plus the strongest base. And this is going to give us sodium sulfate. That's H2O liquid. And so initial here, we'll just drop it down from there, 0.00750. And the initial NaOH is 0.01175. And sodium sulfate is 0. And so the change here, well, the limiting reagent in this case will be NaHSO4. So this is going to go to 0. This is going to be 0.0750 molar. So this is going to give us 5, 2, and then from 7 is 4, 0, 0. 0.00425 molar. And 0.00750 molar. Okay, then we look at what's left over. And what's left over is a strong base, weak base. A strong base, weak base, the pH is going to be dominated by the strong base if it's in high enough concentration, and this is pretty, 10 to the minus 3. This is pretty good. This is going to give us pH around 3, which is, if the pH is around 3, then sulfate, even though that's a dibasic base, shouldn't be too much of a contributor, right? And so we could either go on to the next step. The next step would be the strong, this is a base solution. So what are the major hydroxide contributors? Sodium hydroxide. The next major contributor would be Kb1 for sulfate, followed by Kb2 maybe for sulfate, followed by Kw. So do you want to do those 4 extra steps to figure out how much additional hydroxide? No, probably not necessary. I mean, the pOH is 3, so the pH is going to be like 11. It's going to be pretty significant. What are they asking for? The pH? And so here, if we assume that nothing else has happened, then you see, I wouldn't have solved it. I wouldn't have split, you know, if I'm going to split it up, I wouldn't have written these ionic equation and then ionic necessarily. And so, because HSO4 minus versus sulfate are two totally different species. HSO4 minus is an acid, right? Sulfate is a base. H plus is an acid, strong acid. And so in Chem 1A it might have been okay, you know. Actually, in Chem 1A I try to get people to break the habit of doing that, you know, of ionizing. And so anyway, going back to this is every single titration problem or acid-base problem can be solved in this way. You know, solution dilution followed by strongest acid, strongest base. And so if you don't remember all the shortcuts, you know, millimoles or this or that, then you can fall back on this, right? All right, since I do it the same way, let's try something else. What does the pH of this come out to?
The pOH is 2.37.
2.37? Okay. pOH is 2.37, and therefore the pH is 11.63. Is that correct?
Yeah.
All right. 11.63. All right, let's do the same problem, except we'll make it a little trickier. And so the next example, for this exact same mixture, you know, how many milliliters of, what was it, what am I adding, HCl or? Anyway, okay, how many milliliters of NaOH will it take to get to, let's go to pH of 10.00. I want to get to pH of 10.00. How many milliliters of base will that take? Okay, and so the first thing I have to figure out is where am I? You know, am I, you know, at the first equivalence point, at the second equivalence point, between the first and second, or past the second equivalence point? Where am I? That I have to figure out. Am I past the second equivalence point? If I'm not sure, I'd have to calculate where the second equivalence point is. Maybe I should do that. You know, maybe we should do a quick calculation of where the second equivalence point would be for this particular titration. But you know, if you have a sulfate solution, sulfate's not that strong of a base. You know, we expect the equivalence point to be above 7, but probably less than 10. Maybe not. Okay, and so we need some markers in here about where we are, and the quickest ones would be like, for example, pKa2. pKa2, what did we calculate it? For HSO4 minus, what was the pKa? The negative log of 0.011? 195. And then here's the equivalence point here. And especially at this high of a pH, I would suspect we're past the second equivalence point, right?
Yes.
But let's go ahead and calculate the equivalence point just to be sure. This would be equivalence point 2. Now I had 50 milliliters of, what was it? How much H2SO4 was that?
50 milliliters.
50 milliliters of, what was the molarity?
0.0150.
50.0 milliliters of 0.0150, 0.150 molar, that's right, H2SO4. And I'm titrating this with
NaOH at 0.0385.
385 molar.
Yeah.
All right, and so I need to neutralize both H2SO4, both hydrogens in H2SO4, so how much NaOH do I need to add? And so I have to do a quick stoichiometry calculation, a Chem 1A style stoichiometry calculation to figure this out because I can't calculate it in my head. And so in order to figure it out, this is what? I need 2 moles of, so at the second equivalence point, would be a side calculation to figure out the volume. At the second equivalence point, I have 2 moles of NaOH for every 1 mole of H2SO4. And so this is the mole ratio here. And so what I'll do is I'll just do this.
So 1 and a double.
Yeah, I'm just going to go 50.0 milliliters of the H2SO4 solution. Convert that to liters. I don't really have to convert it to liters because it will cancel out, but I'm going to go ahead and do this dimensional analysis wise to make sure everything works out. And then I know the concentration is going to be 0.0150 moles of H2SO4 per liter.
You get 0.00075 times 2. Sorry, I forgot the last one.
Okay. Just one more. 2 moles for 1 mole. I'll just finish this. H2SO4. And then the concentration of the H2SO4 was NaOH per liter times 1,000 milliliter per liter. So the thousands will cancel. How many milliliters of NaOH will it take to get to the second equivalence point?
I think 38.961.
But how many?
38.961.
961 milliliters. Okay, at the second equivalence point, I'm going to have 38.961 milliliters. Give me more digits because
961.03896.
I'll tell you one drawback of solution dilution is round-off error. The round-off errors, when you do solution dilution method, can screw things up. This is why I try to keep the numbers a little cleaner. All right, so that's how much. Now there are shortcut methods to doing this. You know, once I figure out the volume, then I know it's just a sulfate that I can skip some stuff. But since I'm solving, because I don't want to mix people up, and so I'm going to solve it the same way each time. And so let's go ahead and solve this one. Is that mine? Just check it. All right. So I have my H2SO4, 50 milliliters, and then I'm going to add that much NaOH. And so the final volume here is going to be 50 plus that will be what, 88?
88.96 and all those.
961 ... milliliters. Okay, then I have my H2SO4 concentration, which is going to be the 50 to 88.961. We'll try to go 961 and see if that doesn't round things off too bad. 0.150 molar. And then the NaOH.
Excuse me, it's 0.0150.
Okay, thank you. 0.0150. The NaOH is going to be a 38.961 to 88.961 dilution of. What was that molarity for NaOH again? I should have raised it. 85 molar. All right, and so this gives us what for the H2SO4 NaOH?
Top one is 0.56204. 0.56204.
0.56 is a little big.
Oh, I didn't multiply it by 0.15. Sorry.
0.0084.
0.0084. 3. Give me one more digit. 06.
Yeah.
All right, and then this one.
Sweet, I got the same thing.
Point 01686 0
6,
0.
0. You know what? This works if I just drop this 0, 6 here. That works now. All right, round off didn't affect us too bad. Sometimes it does. This is why I carry extra digits. You don't. Okay, so.
Is there such a thing as carrying too many digits?
Is there such a thing as carrying too many digits?
Yeah, like 9999899976666.
I don't think so. I don't think there's such a thing as carrying too many digits, except it's just a hassle. And they might not be significant, you know. Is it worth knowing pi beyond 3.14? Then maybe there is such thing as carrying too many digits, because people know pi to, I don't know how many digits. But what do we do next? Strongest acid plus the strongest base, H2SO4 and NaOH. So this is going to produce
SO4 minus.
NaHSO4 minus, or NaHSO4, and water. All right, and then we just plug it in. H2SO4, 0.008430. NaOH, 0.01686. And 0. Okay, very, very, very large K for this means that the limiting radius is going to be completely consumed, which is going to be the H2SO4, so we just minus 0.00843. Did this work out? No, it didn't work out, did it?
Uh-oh. How come?
Oh, maybe it did. Yeah, it did work out, sorry.
Whoa.
Relief. Because you know what, it should come out to 0.00843, and it comes out to 0.00843. If it doesn't, then there's slight round off error, and then the next step isn't as clean. When we go to the next step, we take the strongest acid. In this case, it's going to be NaHSO4 plus the strongest base, NaOH. This should give us Na2SO4 plus water.
Okay, 0.01.
Yeah, K is going to be very, very large in this case. And so this is stoichiometric. So both those go to 0, and this goes to 0.0843 molar.
Ooh.
And so we're just left with a weak base, dibasic base. And so the next step would be all the hydroxide contributors. And so the hydroxide contributors would be Kb1, Kb2, and Kw. So let's try to figure out probably we could just go by with Kb1 because we're just looking for pH. Kb2 is probably going to be insignificant as well as Kw. And so we'll just do Kb1 of sulfate. And so Kb1 of sulfate is base plus water. This is going to yield HSO4 minus plus hydroxide. This is Kb1. Kb1 will equal Kw over the K8 for its conjugate acid, HSO4 minus, which is 1.0 times 10 to the minus 14 divided by 0.011, which is going to give us what? Kb1. Wow, that's very small, huh? In other words, it's a very weak base. It's still bigger than water. So sulfate is going to be 0.00843. This is going to be 0, this is 0, water's out. So minus x plus x, dot, dot, dot. So 0.00843 minus x, x, and x. Which means this is going to be x squared over 0.00843 minus x. And the simplifying assumption should work, which gives us an x of what? Times 10 to the negative 8?
Yeah.
Ah, shoot. 8.75 times 10 to the negative 8 means what?
Water.
Which means water
Significant.
water may be a significant contributor to this. Okay? We could see, because the next biggest K would be what? Is it going to be KB2 or KW? Which one will be the next most significant hydroxide contributor, KB2 or KW? Do you guys remember what KB2 is? KB2 was giving us trouble earlier, I think, because KB2 is going to equal KW divided by Ka for the conjugate acid, which is H2SO4, right?
It's very large.
And so, yeah, this would be KW over very large, which means that KB2 should be very,
Very, very small.
yeah. And so, in other words, I would think that KW would be the next one here, because KB2, in other words, it's the conjugate base of a strong acid. Like, for example, chloride. What is the Kb value for chloride? Well, Kb for chloride is going to be Kw divided by the Ka for HCl. The Ka for HCl is very large, so Kb for chloride is very small, which means chloride isn't a very good base, right? And so just like chloride, HSO4 minus is not a very good base. We wouldn't expect it, and therefore we jump straight to Kw, right? Because Kw is 10 to the minus 14. Well, you know, this is a scenario. You know, Kp1 is 10 to the minus 13. Actually, this is almost 10 to the minus 14, right?
Mm-hmm.
True.
Because 10 to the, yeah, it's just about, and so this one and water are going to have roughly the same K value. That means both of them are going to be significant contributors, which means this is going to be, yeah, simultaneous. But just to prove it, well, maybe I'm wrong. Let's just see if H2O liquid would be a significant contributor to the hydroxide here. And so this is going to be initial 0. We'll drop this down, 8.75, and then see how much more water can add to it. Does everybody know why? Does everybody know why skip KB2?
Yes.
Okay.
It's getting us trouble.
Well, anyone else? No? All right. Plus x, so we're going to have x, 8.75 times 10 to the minus 8 plus x. Let me erase this here. So Kw is 1.0 times 10 to the minus 14, which is going to equal x times 8.75 times 10 to the minus 8 plus x. You know, just try the simplifying assumption. If it works, great. If it doesn't, it's okay. that means x is going to be, well, this is 10 to the minus 14 divided by about 10 to the minus 7. This is going to be 10 to the minus 7, 10 to the minus 8. So this is about 10 to the minus 8, which is too big. And so the simplifying assumption fails. And so we have to use the, we have to use the quadratic, which is going to be x squared plus 8.75 times 10 to the minus 8x minus 1.0 times 10 to the minus 14 is equal to 0. So does somebody have a quadratic calculator? Punch that out.
You have one, right, Sam?
6.54 times 10 to the negative 8.
6.54 times 10 to the negative 8. You see your prediction came out correct, that this is going to be simultaneous, because adding that is like going to be close to another 50 or 100% addition, which means what? It's going to perturb the previous equilibrium, and we got to solve these simultaneously. But that's to get a fairly good value for the pH, but we can guesstimate the pH. Well, what's your guess? If water is going to be a significant contributor, the pH has got to be close to 7, right?
Would you say that because NaOH is a little bit stronger molarity, that's a little higher than 7?
Yeah, this has got to be a little higher than 7, right? pH, because this is a base. And so it's just this hair above 7. And so pH is about equal to slightly greater than 7. It can't be below 7 because it's base solution. All right, so that means all that work was to say, oh, we're past the second equivalence point here, right? The pH at the second equivalence point in this titration is going to be a pH 7. Yeah.
So that's how you solve number 37?
37. Yeah, actually, we finished.
You know what weird is, for this one you wanted to solve it for pH 10. I don't know how you got off that.
Yeah, well, we're still working. This is not the 37. This is just a related. I'm just doing a variation, because what we want to do is we want to go to pH 10.00. And so the question is, how many milliliters will that take?
If the 7 is, that's going to take us to 250.
So we set it up. Where are we at? Well, the first thing we have to do is we have to look at where we are at, and if this is a diprotic acid, we expect 1 equivalence point, 2 equivalence points, and then pass. We're in this excess. We're past the second equivalence point, and so we have to know that in order to work backwards, because we got to know where to work backwards from.
Around 7.
Right, and so in this case, we just figured out the pH is around 7 at the second equivalence point. And so we're past that, meaning we're over here. All right, now how do I figure out how many milliliters it'll take? Well, I'll just set it up. So we started off with 50.0 milliliters of 0.150 molar, 0.0150 molar H2SO4. And to this we're going to add plus Z milliliters of
0.0385
NaOH. And so the H2SO4 is going to be a 50 to 50
What's that? A Z?
plus Z dilution of 0.150 molar. The NaOH will be a Z to 50 plus Z dilution of 0.0385 molar. Right? And then we take the strongest acid plus the strongest base. The strongest acid is H2SO4, the strongest base is NaOH. We're going to give us NaHSO4 plus water. That's step one. We're going to call this initial here. This is going to be initial here. And so this is going to be H2SO4 initial. This is going to be NaOH initial. This is going to be 0. Okay. So we have to go past step 1. Going past step 1 means that the sodium hydroxide is going to be in excess, right? You're going to have excess sodium hydroxide. So the H2SO4 is going to go to 0. And so this is going to be, what is this going to be? This is going to be the NaOH, what? Initial minus the H2SO4, H2SO4 being the limiting reagent here, initial. And then the concentration of NaHSO4 minus will just be the same as the H2SO4 initial. And so this is going to equal the, NaOH after step 1. And this will be the HSO4 minus, NaHSO4 minus. Excuse me, NaHSO4 after step 1. Here. Now, what we're going to do is we're going to take the strongest acid present, react it with the strongest base, which is going to be NaHSO4 plus the NaOH. Yeah. And so this is going to be, well, I could either use this or this. I'm just going to plug in, well, this is the same as the H2SO4 initial, right? And then the NaOH concentration here is going to be the NaOH initial minus the H2SO4. H2SO4 initial. This is going to give us sodium sulfate in water. This is going to be 0. All right, then we have to know what the limiting reagent is. This is why we had to figure out where we are in the titration curve, because now you got to know what is the limiting reagent here. NaHSO4, because we're in the excess. We're past, we're in the excess sodium hydroxide region, and so we've neutralized all of this. And so the change here, we're going to lose all of our NaHSO4. That's going to go to 0, right?
Because we're in the excess region?
Right, we're past this, neutralizing this, and now we're in excess base region, right? Past the second equivalence point, correct?
Mm-hmm.
And so this is going to give us NaOH initial minus H2SO4 initial minus H2SO4 initial. In other words, this is just going to be NaOH initial minus 2 times the H2SO4 initial concentration. Well, this is going to be strong base, weak base, and this base is so weak, do you expect it to contribute much? No, because the sodium sulfate is going to be the same as the H2SO4 initial. Here, right? And so this is minus the H2SO4 initial, minus H2SO4 initial, plus H2SO4 initial. Is everybody following along? And so this is going to, well, we just plug in. We do the substitution of that and just solve for Z. And so this is just like the earlier problem we solved, except there's just one extra step in here. All right. there's got to be a big jump because at the second half equivalence point here, right, this is the half EQ point 2. At the second half equivalence point, it was pKa2, right? pKa2 calculated as 1.95, is that correct?
Mm-hmm.
That's very low, so there's got to be a big jump here, you know, because we're going from 1.95 up to 7 to 10. At 1.95, if that is the, are we going to see this first?
Probably not, so it's kind of around
Yeah.
0.5 or 0.8.
Yeah, it's going to be very low. It's going to be hard to see that, especially at this concentration. We'll just see 1. All right, is this okay for solving? Just solve for Z?
Yeah,
Yeah? You give it to him.
I guess so.
All right, now let's do another one. I want to go to a pH of, this is 1.95. I want to go to pH of 2.95. If I want to go to a pH of 2.95, what is it? Actually, these numbers aren't clean. I should do it on a cleaner set of numbers, but it would be, well, that's pKa plus 1, which would be the, what we call the, what did we call that? The 10/11th equivalence point. And so what I do is I divide this volume here into 11 parts and take 10 of them. That would be the 10/11th equivalence point, right? But what if I'm at a number that's not so easy to figure out? And so what if I want to go to pH of 3.42? How many milliliters do I have to add? You know, well, at a pH of 3.42, what region are you in? You're in the buffer region, right? And there are two ways you could solve this. One way is we could work backwards, like we've been doing over here. The other way is we could do the shortcut method. Here. And so we'll try this. We're going to work backwards first, and then do the shortcut method second. All right. So working backwards, if we know that we're in the buffer region, then the difference in this setup is this. We haven't neutralized to the second equivalence point. And so if we haven't neutralized it to the second equivalence point, that means that the sodium hydroxide is the limiting reagent now, and the NaHSO4 is the excess. And so the difference that this makes in this is that now we're going to be minus NaOH. We're going to lose all of this. Minus NaOH here. And then this is going to be the H2SO4. This is initial minus the NaOH initial. This is going to go to 0. And then over here, the sulfate is going to be plus NaOH. NaOH. Initial. And so what we have left over here is a weak acid and its conjugate base. In other words, what we have left over is a Henderson-Hasselbalch buffer. If we have a Henderson-Hasselbalch buffer left over, then the pH is equal to, the pKa of this acid, which would be HSO4 minus, plus the log of the base. The base is going to be the sulfate over the acid, which would be the HSO4 minus, right? Higher. Then we substitute those in and then solve for Z. Okay, you have an announcement?
Hey, hi everybody. So
Good morning.
good morning. So last Thursday, I didn't show up to the workshop because I had to prepare for a test for organic chemistry. So we weren't able to do any type of chapter 17, even though we did some stuff on Tuesday. So we're a little bit behind with what Dr. Chabal is doing. I do understand you have a test on Thursday.
Next week, Tuesday next week.
Oh, you switched it to next Tuesday?
Yeah.
Okay then.
But I'm finishing up chapter, so I was actually supposed to get into chapter 18 today, but I'm still working on 17, so.
Okay, great. So there's no alarm then. We can pick up from where we left off, and we'll still be able to move at a decent pace, but not too fast, but be able to be on match with what he's doing. So same as everything, workshops on Tuesdays and Thursdays from 12:30 to 1:55. Any questions, ask me now. And everybody in here should have a chapter 17 worksheet. So tomorrow for sure we're gonna cover how much of a particular salt you may need in order to get a particular pH of a buffer solution. We're gonna cover things like that. And we're also gonna do acid-base titrations. And we'll probably do diprotic acid-base titrations on Thursday. And that'll be the end.
Okay,
All right?
that sounds good. Sounds cool.
Okay, thanks guys.
Thanks.
Uh-huh.
Okay. So, this is, the standard method. But when we're in the buffer region, we can use the shortcut methods as well. And so let's let me show you how you do. Speaking of shortcut, the only shortcut I'm showing you is for the buffer region because that saves a lot of time here. In the buffer region, do we have to worry about solution dilution? No, we don't, although we did it here. If you do it the standard method, you got to do it solution dilution. But here, we know that to reach the first equivalence point, it takes volume 1. To reach the second equivalence point, it takes another volume, volume 1 again. And so 2V1. And so to reach the second equivalence point, in total will be 2V1s, right? Or volume 2. Now, here, if we want a pH of 3.42, we're in the second buffer region. And so pH 3.42, the first thing is we're in the second buffer region. The first buffer region would be H2SO4 and HSO4 minus. But this is not good because this is a strong acid, and therefore this is not really a buffer, right? In this region here, we have HSO4 minus, a weak acid, right? And SO4 2 minus, a weak base. But we're going to call it the second buffer region because it's diprotic, and we got to think in this way to get it. And so this is the only reason I didn't want to do. I was thinking that maybe I shouldn't do H2SO4. Whereas a regular diprotic weak acid would have a first buffer region and a second buffer region. Right? All right, and so now we're in the second buffer region. We want a pH. The pH is equal to 3.42, and this is going to equal the negative log of the Ka. Actually, we got the pKa1, which was 1.95, plus the log of the ratio. This is going to be the sulfate to HSO4 minus ratio. And so we solve for the sulfate to HSO4 minus ratio here, which is going to equal, subtract that from both sides.
1.47, and then that inverse log, right? Or the 10.
10 to 1.47?
Yeah.
Okay. And so what does that come out to?
29.512.
29.512. All right, now comes a trick. So this is going to be 29.512 over 1. And so the way I think about this is I've neutralized 29.512 parts of the HSO4 minus and converted those into base. That leaves me with one remaining part left over. And so then I need to convert this into an equivalence point. To convert this into an equivalence point, it's going to be the 29.512 out of 30.512 total parts. And that leaves us with one remaining out of 30.512. And so this is what we call the equivalence point here. And so I'm at the 29.512 divided by the 30.512 equivalence point. And so all I do here is I'll take 29.512, and this is the volume here that I need, right? Over 30.512 times the volume, whatever that volume was. Now the volume was 38 to reach the second, so divide that in half. 38 divided by 2 would be what, 19? So this is going to be about 19, and so it's going to be close to 19 milliliters, right?
I got 18.37.
18.37?
Yeah, with that number.
Okay, 18.37. And so the volume that it takes to get here is V1 plus this. And so that would be 19 plus the 18, which would give me that, right? The total volume.
37.3.
37.3?
Yeah.
Okay.
37.
All right. And so we have to add these two volumes here. Does that make sense, or am I skipping too much? Skipping too much? All right.
Okay, first of all, what's the study of 9.512 means? And I don't get what you're doing at the equivalence point.
That's just a ratio of how much SO4 minus to HSO4 there is. On the right, is what you're talking about?
Yeah.
And then you divide that by 1. And then,
Am I out of time or what? 5 minutes? I think the problem with this is the numbers. The volumes aren't clean. Let me do some simple volumes. Because the volume, since the volumes aren't pretty, the numbers come out all complicated. But let's say it takes 10 milliliters to reach the first equivalence point.
How much does that?
Then, yeah, how much to the second? 20 milliliters to reach the second. Now, the first equivalence volume will be 10 milliliters, and the second equivalence volume will be 10 milliliters. It takes 10 milliliters to neutralize per equivalence point, right? And so, what I have here is this. I'm going to be looking at the ratio of base to acid here. Okay, over here I have all base, all acid, no base. Over here I have all base, right? And so this is going to be 100% acid. This is going to be 100% base. Now, in my mind, I look at this 10 milliliters. Over here at the starting point, I have 100% acid. At the finish line, I have 0% acid. And over here, I have 0% base and 100% base. And so this is what I'm thinking in terms of the ratios. And so in terms of ratios, if I'm at a 50-50, let's say halfway between your A and B, this is 50%, this is 50%. It's a 1-to-1 ratio, right? Or if I'm at 25% A, what percent B must I be at? 75% B. And so, thinking about this. Well, if I'm at 25% A, then we call that the 1/4 equivalence point here. All right, this is the 1/2 equivalence point. And then on, you know, this is 75%. Oops, am I going backwards? I'm going backwards, sorry. This is 75%, 25. This would be 25%, 75%. All right, so this is the 1/4 equivalence point, right? But look at the ratio. The ratio is a 1-to-3 ratio. Or actually, it's the 3-to-1 ratio, but in terms of base to acid, it's a 1-to-3 ratio. So 1-to-3 ratio is a 1/4 equivalence point. And so what we do is we got to figure out how this ratio relates to the equivalence point. And so how this ratio relates to the equivalence point is like this. So if I'm at 25% B and 75% A, and so I got a ratio of 25 to 75, right? This would be called the 1/4 equivalence point. Well, how does 1/4 factor in there? 1/4 factors in there because this 25 to 75 is the same thing as saying 25 out of 100 parts have been converted into base, leaving 75 out of 100 parts unreacted acid. And so the 1/4 is this. This is what we call the equivalence point. Because this shows 1 part out of 4 have been reacted. And so that's all I did, but the numbers were, and so what I did was I went from the ratio, this is the ratio we got from Henderson-Hasselbalch, and then I did one extra step to figure out what the equivalence point is, which is going to be the numerator up here. And so that's, assuming the numbers are right, 29.9 out of, what was it, 38 over 39 or something like that?
30. Wait, what's the?
No, it couldn't be that big. It had to be 18, so it was 18 over 19, something like that. And so if we, let's say we're left with a ratio of 18 out of 19, then that means what? Was that right? Or 18 out of 1, I forgot. It was 29 out of 1, okay. And so this gives us 29 out of 30 reacted, 1 out of 30 unreacted. This is our base, this is the acid. So we've converted it into base down here, starting off with 0, right there. Does that make sense?
Okay, but where did the denominator came from?
Total parts.
The denominator part comes from the amount of acid that's unreacted. So in other words here, if I'm at the, let's say I'm at the 7/8 equivalence point, what's my ratio of base to acid? If I'm at the 7/8 equivalence point, what is the ratio of base to acid?
7 is the ratio of the base. 8 is the ratio of the acid.
No. 7/8 is the ratio for the base, and 1/8 is the acid, and so this gives me 7. Is the ratio 7-to-1 ratio? So if I'm at the 7/8 equivalence point, I'm at a 7-to-1 ratio base to acid. Okay, is what it means. And so that's the only thing about the shortcut is you have to know the ratios to figure it out. But anyway, stop here.